But before we go ahead and do the backwards pass, let's just reiterate what happened in the forward pass computation. We added the activity times along each path in the network. We took the early start plus the duration of that activity to get the early finish. We carried the early finish to the next activity where it became its early start, unless the next succeeding activity was a merge activity, in which case we used the largest early finish from all preceding activities. So these things you'll have to try on your own to really get practice on. Now we've taken and done a backward pass through the network by starting all the way over on the right-hand side at 235, subtracting 35, and getting 200, and then filling that in as the late finish time for each activity, subtracting duration, getting a new late start, and then the only problem comes into play is when you have multiple activities merging, if you will, backwards. So the first place that happens is in activity B. You have 185 days coming out of activity E, and 20 days as the late start coming out of activity F. In the backwards direction, you always use the smallest number. So you see that when we have a choice of 185 or 20, for construction plans we put 20, and so on down the line. Same thing happens again in activity A. You see activity D has a late start of 15 days, and activity C, late start of 10 days. Activity B, a late start of 5 days. So you have to make a decision which one to use when you're running a backwards pass, and you use, again, the smallest number. So 5 goes into the late finish for activity A. So what you saw happen there in the backwards pass computation is we subtracted the activity times along each path of the network. We took the late finish minus the duration of the activity to get the late start. We carried the late start to the next activity where it became the late finish, unless the next succeeding activity is a burst activity, in which case the smallest late finish of all preceding activities is selected. From this analysis, we can start determining some things about the project network. And the first thing we can look at is the free slack or float. And by definition, it's the amount of time an activity can be delayed after the start of a longer parallel activity or activities. It's also how long an activity can exceed its early finish date without affecting the early start dates of any successors. And it's a place where you, as a manager, can figure out where to start using and managing scarce resources. Project sensitivity is the likelihood of the original critical path changing once the project's initiated, and also looks at things like whether there's lots of critical paths within the network and where they merging together, where they're separated. So basically, when you've got critical paths or a lot of near critical paths, your project network is considered highly sensitive. Looking back at our example, we can figure out the slack, and the slack is nothing more than the late start minus the early start, or the late finish minus the early finish. And you can see that slack exists in many activities on this network and doesn't exist in some places. The place where the least amount of slack exists, and that's typically where there's no slack, will be the path that's known as the critical path. So you can see in this particular network, the critical path is A, B, F, G, H. All other activities have slack in them. Now we have to distinguish between the slack of an activity and the free slack an activity has. And we're going to try that on the next slide. The author has gone through several iterations of this since I've been tracking this textbook. And so we'll give it an attempt here. But the main thing has to do with where that slack is and who manages the slack within the project network, and in some respects gets into project culture and project management culture and things of that nature. So let's take a look at this example. And there was no good example of total slack and free slack in the last project network. So we're going to look at this project network here. And what you can see, of course, is the critical path runs from activities 1 through 4 to activity 6. And you can see where there's slack in certain activities. Build hardware, 17 days of slack. Code software has 16 days of slack. But notice it has no free slack. Again, free slack's a slightly different animal because it's really, if you think about what the definition of free slack, and that's, how long can this activity be delayed where it doesn't delay things downstream? Well, if I take any slack up and build hardware, or take any of the slack up and code software, the people involved with testing the hardware, probably a different organizational part of the company, would need to know about that, because they're not going to be able to start their activities on their early start date anymore if you don't do your finish on the early finish date. But looking further on at the test hardware, test software, which may become out of two different areas, they're running parallel according to this network, they've got own all the free slack for this activities in the project network, because beyond that point is testing the network. And so as long as both of those get done prior to activity 4 being completed, there's no need to notify people downstream. Those people involved in managing the software testing and hardware testing can run independent of the network folks if they need to in this particular project. So there's where that distinction between total slack and free slack comes into play. I know it's a little confusing. I'll be the first to admit that. The good news is it doesn't come into play much, at least in the testing in this class. And in reality, there's way more dynamics about who owns slack on activities than comes up in the project network. Let's take a look at another example. Now, these examples here are more paralleling the output you see in Microsoft Project 2007. In fact, this is the project network here for this air control project, and I think you have a similar project in the video examples. You can see the start date, the finish date, the duration, the ID. If there were resources identified, they'd be on that project network as well. In this particular case, because of the slide colors, the critical path is actually in white. So the critical path in this network is activity 1 through activity 4 through 6 through 7 into 8. So just another way of representing, not quite in the format when you're drawing these out by hand. What's important about this is being able to understand and looking at the project network, trying to see the relationship between the project network and what we can create, which is called the Gantt chart. And in the Gantt chart, we can see all the information that is representing in the project network, but we can see some more things visually, or a little easier now in the Gantt chart. And one thing to be careful of is, if you notice the start and start dates, although the duration is 2 days for the first activity, we won't start the next activity until the following date, even though if you look at if you did a backwards and forward pass through this network, these 2 days and 15 days would appear and almost think like you can do them more concurrently. But there is some precedence to the order, and when does one day start and another day begin gets into a little bit of a esoteric discussion. But be that as it may, once we put the calendar dates in, it's pretty clear to see that the Gantt chart puts in and forces things in the right dates based on a normal working day of 8 hours, at least within Microsoft Project, unless you switch the hours around. And what you can also see here is, in this case here, the critical path is the gray bars linked together. And what you more importantly see is the free slack, or the slack available on individual activities, and they're represented by the line that shows between the particular activity and connected to the next activity. So looking at the pink bars in the Gantt chart, you can see there's a bit of space there that can be used to manage the project and manage these activities. Some additional project networks that come closer to representing reality involve the use of laddering and lags. In laddering, we'll break up the activities into segments so that we can actually get the work done sooner, and I'll show you an example of that in a moment. But let's also look at lags. And if you think about it, and I might have mentioned it in an earlier slide, activities and work sometimes involve waiting around, and lags allow you to program in those waits without them taking up valuable duration time within the activity itself. They're sort of cruel to do by hand when we do project networks, but they're really easy to do within Microsoft Project, and you'll get to do that as part of the case, I believe. So laddering technique is used when you have some sort of relationship between activities, but there's going to be some delays, and instead of, in this example here, instead of trenching out for a pipe all full miles, maybe you trench the first third and then allow for people that are going to lay the pipe to start laying pipe in while you start trenching the second third. Once you get far enough along, you can actually start backfilling where the pipe's been laid. And so instead of trenching out a full mile, then laying a full mile of pipe, and then refilling a full mile of the ditch that you dug, you break it up into segments that allows you to get it done safely and maybe faster because you didn't wait the full duration to go ahead and do your work. So earlier I mentioned lags, and there can be all sorts of relationships, and the lags is the time delay, and whether the delay is because you're waiting for processes to be completed or waiting for design work to be done or whatever the case may be. Maybe you're waiting for a supplier to deliver the goods to your manufacturing floor, whatever the case may be. And those relationships can exist lots of ways. They can exist in the case of the first example, a finish to start lag. Maybe we are going to wait and start an activity after a while, after other activity's been started, in a start-to-start relationship. Going back to our example of the trenching, maybe we'll lag 3 days between the trenching before we start laying the pipe, and then we'll lag 3 more days before we start refilling it. So again, that's a start-to-start relationship. Some additional example of lags are a finish-to-finish relationship. You might have a lag between the time the prototyping is done and the time you expect the testing to be done. You can have a start-to-finish relationship between two items. And you can have some sort of a combination relationship, all legitimate. Very easy to program within Microsoft Project, very challenging to do by hand. If you really want to be challenged to do it by hand, you can try and confirm that this is the exact project network for this particular very simple 5-activity network, but I don't necessarily recommend it. I don't make you do this by hand on any examination. This would be something that would be ideal for putting in some project planning software. If we look at our traditional sequence for new production, new product planning, we would plan the product, then do some systems engineering, then do some design and development, then do purchasing and procurement, then we'd manufacture, then we'd do some QA, and then release the product. Well, in that thinking, if this is truly a linear relationship, it will take a long time to get products to market. So a lot of new product development is doing more of a concurrent approach, where we'll take a risk that we'll have enough of our planning done so we can start our systems work. While product planning is ongoing, we'll start working on systems engineering, and we won't finish systems engineering while we get into design development, but it'll be far enough along that we'll be comfortable that we won't be looping backwards. Of course, you're drawing a big risk that you might have to redo or actually create some backwards loops that cause other havoc on the project network. But at the same time, look at the relative distance, if you will, between getting a product out under the conventional sequential approach versus a concurrent approach. You can see a significant savings in time, assuming that it's worth the risk and the potential of having to do some additional work. Well, that was a lot for Chapter 6. I'll be the first to admit it. There's some good resources available to you. Take a look at the example files, and hopefully between the time you see all this and next time, you'll be able to handle project networks, putting simple networks within Microsoft Project, and all the technical details handling project networks before we start thinking about putting resources in. We won't see that for another couple chapters, but that's really where the rubber hits the road. See you next time.